Okay, hello everyone. Good morning, all of you. So we start with the quote. If you want something you have never had, then you have got to do something you have never done. If you have a routine life, if you want to have a routine life, you just lead your routine life as it is. But if you want to do something or if you want to achieve something, then you have to live in a different fashion. And if you want something you have never had, then you have got to do something you have never done. Okay, but if you want to do in the same way, if you want to live in the same way, your life will be in the same way. There will not be any change. Okay, and today is the birthday of James Watt. I think everybody is familiar with him. He is Scottish engineer and inventor whose steam engine contributed substantially to the industrial revolution. Okay, this is the main invention which changed the whole world. Actually, this is what is industrial revolution. They came into picture. Okay, it changed the scenario of the whole world. In 1763, he repaired the model of Newcomen's steam engine belonging to Glasgow University and began experiments in properties of steam. The Newcomen engine was simple in design. It acted as a pump, and a jet of cold water was used to condense the steam. But Watt improved on this design by adding a separate condenser and a system of valves to make the piston return to the top of the cylinder after descending. He took out patent for the separate condenser in 1769. He later adapted the engine to rotary motion, making it suitable for a variety of industrial purposes, and invented the flywheel and the governor. Okay, so much contribution in the invention of steam engine. So actually, as I told, this changed the whole scenario of the world. Okay, today we will have the partial differential equations. So we have seen till the last class that the every fluid flow in the nature are governed by the conservation equations, which are partial differential equations. So if we can understand the behavior of partial differential equations and how to solve the partial differential equations, then we'll be able to solve any equation which gives the secrets of the whole nature. Okay, so that is the idea behind the CFD, and we will see the classification of partial differential equations. So we classify them based on the highest order derivative of the equation. So you can have first order, second order, third order, like that we can have based on the highest order derivative present in the equation. We say it is first order equation, second order equation, or third order equation, etc. And then based on the degree of the highest order derivative, okay, present in the equation. Okay, again, it can be first degree, second degree, etc. Okay, suppose if I have something like pi xx plus pi x whole square plus phi equal to 0. If this is the equation, what is the degree of the equation?
2, sir.
2. Okay. Is it 2? What is the highest, the order of the equation?
Order is also 2, I guess, because it's 5xx.
Order is second
Order
order.
is one.
If
Order is 2, degree is 1.
degree is 1 only, because it is not
The
the
highest
degree
Rodogio also got a god.
it is the degree of the highest order derivative. So this is 5xx only. There is no degree for this. So it is first degree equation. Is that clear?
Yes, sir.
Yeah. And then we have homogeneous and non-homogeneous. If there are if no terms without dependent variable, then it is homogeneous. If every term in the equation has dependent variable, then it is homogeneous equation. If there are some terms without dependent variables, only independent variables, like okay, I will tell you like this general equation. Later we are going to analyze that also. Suppose I have some a phi xx. Yes, this is the generalized second order equation, linear. So a, b, c, d, e, f, g are functions of x and y. Okay. A, B, C, D, E, F, G can be functions of x and y. Anything like it can be sin x, cos x, e power x, log x, anything, or log y, or x square y, like that. Anything it can be. So they are, and here x and y are independent variables, and only phi is the dependent variable, which normally we are interested in solving. Okay, so if now if it is to be homogeneous, is it homogeneous or non-homogeneous? Normally people see that if equal to 0 is there, it is homogeneous. It's not that actually. There is g is here without any dependent variable there. G is only having independent variables. It can be functions of x and y. Okay, so if g equal to 0, then it is homogeneous. Am I clear about it?
Yes, sir.
Yeah. And then the more important thing is linear or non-linear. Or another thing also is there, quasi-linear and non-linear. Okay, when do you say a equation is non-linear?
When the order is not equal to 1.
No, it's
No, the degree is not equal to 1.
okay. Here, if there is any term with product of derivatives, product of, okay, I can say product of dependent variables or its derivatives, then it is non-linear. Like okay, phi square, it is non-linear. Phi x, non-linear. Okay, and okay, phi x, phi y, non-linear, and okay, phi x whole square, phi x. So like this, if there are any terms like this, they are non-linear. Is it okay?
Yes, sir.
There should not be any product of dependent variables or its derivatives. Then it is, if there is a term like that, then it is non-linear. Otherwise, we can say it is linear. Quasi-linear, sometimes people use it. If the coefficient of highest order derivative is a dependent variable but of less order, then it is quasi-linear. That is, if I have this, okay, this is quasi-linear term. Phi xx is the highest order derivative, suppose, then multiplied by phi, though it is non-linear, we say it is quasi-linear. It is not linear, but it is quasi-linear. Is that okay? The highest order derivative, if it is multiplied by some dependent variable, immediately we say non-linear. But non-linear equations are very difficult to solve. But if the coefficient is less than the highest order derivative, then it is called quasi-linear. Sometimes they can be solved. Okay, phi xx whole square is completely non-linear. If it is second order derivative, the second degree equation, then this is non-linear. But phi xx is quasi-linear. Is that clear?
Yes, sir.
Yeah. And the next classification, actually, which we are interested in, we are going to spend time on that. The equations can be elliptic, parabolic, or hyperbolic. Okay, so this we are going to concentrate on. And there are some more classification, like some problems are called equilibrium problems and also called jury problems. And mostly elliptic equations are equilibrium problems or jury problems. And they are sometimes called as marching problems or propagation problems. Usually parabolic and hyperbolic equations are marching type or propagation type. And there are another problems called as eigenvalue problems. These are also elliptic only, but they are found in solid mechanics. We don't discuss about the eigenvalue problems. Solid mechanics. Usually vibration problems or structural problems like buckling, etc., or resonance. Okay, these problems are eigenvalue problems. Okay, we are interested in these two types of particular problems. Okay, so we will see how to classify mainly this elliptic, parabolic, and hyperbolic, and we will see what is the physical behavior of those equations. Okay, as I told, we will take second order equation with two dependent variables, sorry, independent variables. Okay, so a phi xx plus b phi xy plus c phi yy plus d phi x plus e phi y plus f phi plus g equal to 0. This is the equation. So here there are what are called as characteristics. Okay, these characteristics, these are the curves which are the solutions. And along characteristics, the highest order derivatives are indeterminate, and across the characteristics they are discontinuous. Okay, these are what are called as characteristic curves. These are the curves along which the highest order derivatives are indeterminate and across which they are discontinuous. Okay, so I want to have the value for second order derivative or the highest order derivative from this equation. So what I do is I will write this as a phi xx plus b phi xy plus c phi yy. I take all the other things to the other side, minus d phi x minus e phi y minus f phi minus g. And all of this I will write it as some h, just for convenience. Okay, I want, because if I want to have the expression for a second order derivative, I should have two. How many unknowns are there? 3 unknowns, phi xx, phi xy, phi yy. So I want to have 2 more equations to be generated. So how I do it is, I will take d phi x is equal to, okay, suppose f is equal to a function of xy, df is equal to dou f by dou x into dx, dou f by dou y into dy. In the same way, d phi x is dou of this, dou by dou x of this into dx plus dou by dou y of this into dy. Okay, dou by dou x of d phi x is phi xx into dx plus dou by dou y of this, that is phi xy into dy, is equal to d phi x. In the same way, if I take d phi y, d by dx of this is phi xy into dx plus d by dy of this is phi yy into dy. Like this I will get. So I have generated 2 more equations which are having second order derivatives. Okay, so using these 3 equations, I try to find out what is phi xx or phi xy or phi yy. Okay, so how to find out that? Using Cramer's rule. Okay, I write phi xx as ratio of 2 determinants, and the denominator contains coefficients of the dependent variables or the unknowns. Okay, what are the coefficients? A, B, C, dx, dy, 0, 0, dx, dy. A, B, C, dx, dy, 0, 0, dx, dy. And in the numerator, these 2 will be as it is, B, C, dy, 0, dx, dy. And the first column will be on the right side, whatever I have. Right side I have h, d phi x, d phi y. Am I clear about this?
Sir, I want to learn about the previous steps. Yeah, sir. How did you write these 2 last equations?
Okay, d phi, see, like f is a function of xy. Okay, then df I will write it as dou f by dou x, that is fx dx, plus dou f by dou y fy dy. Is that okay?
Yes, sir.
In the same way, d phi x is written as d by dx of d phi x is phi xx. So phi xx dx.
Okay, sir.
In the same way, phi xy dy. Similarly, if I take dfy, x derivative is phi xy now, phi xy into dx, y derivative phi by y into dy.
Okay,
Is
sir,
that
got it.
right?
Yes, sir.
Okay, so this is the way I will get the phi xx. Like similarly, phi xy, phi y also I get. So all of them will become indeterminate when this denominator equal to 0. And this is called the okay. So this is called the equation of the characteristic. Okay, and these characteristics, that is the solutions, right? So this should be equal to 0, and if this is equal to 0, this is what is called as hodograph. Okay, we are not interested in that, but just terminology I'm telling. This is hodograph, and this is the characteristic. So I have to equate this to 0 so that I get the equation of the characteristic. So how to expand? You expand it, a into dy whole square minus b dx dy plus c dx whole square is equal to 0. Okay, divide by dx whole square. So a dy by dx whole square minus b dy by dx plus c equal to 0. So the slope of the characteristic I can get dy by dx is equal to b plus or minus root of b square minus 4ac by 2a. So now if b square minus 4ac is less than 0, so both characteristics are imaginary. And these types of equations are called elliptic equations. So if b square minus 4ac equal to 0, only one real characteristic, and this is called as parabolic. And similarly, if b square minus 4ac greater than 0, two real characteristics, and these are called as hyperbolic in nature. These are called as hyperbolic in nature. Is this clear?
Yes, sir.
Yes, sir.
Okay, this is the way we classify if I have second order equations. We will see some of the examples. Okay, suppose it should be like a phi xx plus b phi xy plus c phi yy is equal to something I have. Okay, if I have that, so the coefficient of phi xx is a, and this is b, and this is c. I want the value of b square minus 4ac to decide whether a equation is elliptic, parabolic, or hyperbolic. Suppose if I take now del square phi equal to 0 or del square psi equal to 0, which is called as Laplace's equation. So we know these equations are for 2D incompressible irrotational flow. Okay, these equations we have derived. So what type of equations these are? This is phi xx plus phi yy equal to 0. So what is a now? A and b and c. What is a?
A is 1.
A is
1.
1.
B
B
is
is
0.
C is
C1.
1, right? So what is b square minus 4ac?
negative.
Negative.
Minus
It
4.
is zero. Okay,
Negative.
that's the answer. So this is elliptic in nature. These equations are elliptic. Okay, what is the basic characteristic of elliptic is? So I don't have any particular direction of propagation. Okay, the solution or the information, how it propagates, I don't have any proper direction. That is because the characteristics are imaginary. Okay, so it is like and we know that this is incompressible irrotational flow. So in a fluid, if you give a disturbance, right, in the water, if you put a stone, so what happens, how the information goes, how the disturbance moves? It moves in all directions uniformly. There is no particular direction. Okay, so those types of problems are elliptic problems. There is no particular direction for propagation of the disturbance. It goes in all directions uniformly. Okay, such are elliptic equations. So all incompressible flows are usually elliptic in nature. Okay, so the disturbance moves uniformly in all directions. Okay, and another thing is these problems are called as equilibrium problems or jury problems. Okay, what it means? Usually these are also called as boundary value problems. And the domains are closed domains. It is like, suppose, even in the heat transfer, now you are studying the heat transfer, you have del square T equal to 0, unsteady 2D conduction problem without heat generation. Suppose if I have this, so what is the heat transfer equation? Alpha del square T plus some Q dot or something, or Q, whatever you write in the heat transfer. So there is no heat generation, and it is it is steady. Okay, steady problem. So this is 0. So del square T equal to 0, and this is elliptic in nature, right? So if I have a rectangle, suppose, right, and so if I am given the boundary conditions here, I can find out the temperature distribution in the whole domain. Okay, so this temperature within this depends on only the values on the boundary. Okay, so that's why it is called as boundary value problem. I should be given the boundary conditions on all the boundaries. Then only I can solve it. So this is a boundary value problem. And also this is a closed domain. Okay, what do you mean by here Txx plus Tyy equal to 0? So how should be the boundary conditions? T should be prescribed, T or derivatives of T are to be prescribed at two values of X. So that is on this boundary, on the left boundary and the right boundary. In the same way, the T is to be, T or derivatives of T are to be prescribed based on Dirichlet condition or Newman condition or Robin condition. At two values of Y, it is to be prescribed. Then only it can be solved. So all the boundaries, it is to be prescribed. That's why it's called as boundary value problem. And the boundary is to be defined clearly. So it is a closed domain. Okay, if it is time domain problem, then the time will be open. Okay, I don't have time derivative here, only space derivatives. Okay, so this is also called as, and another thing is jury problem. Okay, equilibrium problem means it is a steady state problem, and jury problem means the values depends on only its boundaries. Okay, suppose I have 100 degrees here and 200 degrees here, 300 degrees here, 400 degrees here, suppose something like that. Or derivatives also can be given. Suppose it is a Dirichlet conditions. Any value of temperature within the domain cannot be greater than the maximum on the boundary and cannot be minimum, cannot be less than the minimum on the boundary. Am I right or not?
Yes, sir.
So it cannot be more than 400. It cannot be less than 100 when the boundaries are fixed with some values like that. So this is confined by those boundary values. Okay, this is the characteristic of elliptic problem. Okay, now
That is only when there is no heat generation term or heat sink term.
yeah, there is no heat because then it will be poison. Okay, and if I have even if I have the heat generation, del square T is equal to some Q like this. This is what is called as, what type of equation it is called as? It is called as Poisson's equation. If it is equal to 0, it is Laplace's equation. If it is something there, it is Poisson's equation. And this is also elliptic only. This is also elliptic only. Am I clear? But only thing is, okay, here it is not exactly as I told. It is it cannot be more than the maximum or it cannot be less than minimum. If there is heat generation, anyhow the boundary conditions define the values in the domain. Okay, so that is the equilibrium problem or Jury problem. Okay, Poisson equation also elliptic equation. There can be heat generation, but still it is elliptic equation only. But this particular property which I told, it will not be exactly same. Okay, if there is heat generation, it can be more than what time, because I am not, when there is heat generation, I am not what can I say? Okay, leave it. So, okay, if it is all Dirichlet conditions, whatever I told, that is right. That is, cannot be more than the maximum and less than the minimum. If there is heat generation, it can go beyond that. Okay. And then these boundary conditions will not be right also, because the values, the temperatures on the boundary cannot be fixed like that if there is heat generation, right? Okay. So the next thing is about parabolic. Okay, so parabolic, when it is parabolic, b square minus 4ac equal to 0. Suppose if I have unsteady 1D heat conduction, and again without heat generation. Okay, so I have T is equal to alpha del square T squared, and this is not there. This is there, but this is one dimensional. So T is equal to alpha dou square T by dou x square. Okay, so this is the type of equation I got. Now, what are A, B, and C?
C is 0, A is 1, B is 0.
Yeah, A equal to 1, B equal to 0, C equal to 0. So then what is B square minus 4AC?
0.
0. So this is parabolic in nature. This is parabolic in nature. And so this is something like a fin problem like thing. Okay. And suppose I have given the initial condition here. And so this, if I am getting, suppose heating it, it is going to change all the values along the fin. Okay. So I have to be given the, and also because this is what is I called one-way coordinate. So it is going to change in time. Okay. So, and the time domain is open. That's why it is called as open domain. At only one value of t, I am going to prescribe, and at two values of x, I have to prescribe the temperature. So at this point and at this point, I have to give some boundary conditions for temperature. And in time domain, I have to give at one particular point of time, because it is first order derivative. Okay, many times people don't know how many boundary conditions are needed or how many conditions are needed. This is called as actually initial boundary value problem. Okay, initial conditions are to be given, and boundary conditions at 2 boundaries I have to be give the conditions. Okay, so this is a parabolic type, and okay, and even in momentum equation also, I can have something ut is equal to mu exx. Okay, like this. If all the other conditions are negligible, so because I know the general equation is ut plus u dot steady 1d discuss like this. Okay, so here actually on the right side in the diffusion term we have mu del square u, but in that 1d, so only uxx will be there. Okay, and here actually it should be there like ux also should be there, u dou u by dou x mu uxx like this. So there is no pressure term, and even this term is small or negligible, then I will have this particular equation. Okay, so under some assumptions you may get this type of equation. In the momentum equation may become this type. So then also this is parabolic because it is similar to that. So this is one important thing actually, whether I solve del square phi equal to 0, del square psi equal to 0, del square t equal to 0, right? If I write an program or code to solve this, I can solve these also. Everything, the code will be same. Only thing, the boundary conditions will be different. The values of phi on the boundary will be different. Psi on the boundary will be different. T value will be on the down. So whatever you prescribe there, you are going to solve that particular dependent variable. Okay. Okay, this is parabolic. So parabolic, this is marching problem. These are called as marching problems because I march in time. There is one way coordinate is there. There is a particular one way coordinate. Whenever there is a one way coordinate, then I can solve it by marching method, and this is called as marching problem. So parabolic problems are marching problems. And so if I have something like do you know what is this equation called as? Anybody?
Diffusion.
Wave. This is called as second order wave equation. Okay, so if I have an equation of this sort, so I will write this as utt minus a square uxx equal to 0. So what are ABC here? A equal to 1, B equal to 0, C equal to minus a square. Right? So B square minus 4AC is
Positive.
4A square. Right? And this is greater than 0. So this is hyperbolic.
Sir, one doubt, sir.
Yes.
Like usually there are three variables x and z, but we are considering x and y. In the previous case, we considered x and y.
Yeah.
And here we have x and t.
See, x and t. Okay, it doesn't matter. There are two independent variables.
Yes, sir.
Okay. So it need not be x and y. It can be x and t.
Okay.
Okay. Only thing is in the previous case, time derivative is only first order. That's why it will not come into ABC.
Right, sir. Right.
Okay. And and sometimes you cannot say there may be a parameter based on which you decide whether this is elliptic, parabolic, or hyperbolic. If I take velocity potential equation, for compressible flows. For incompressible, del square phi equal to 0. But for compressible flows, it will be like this. Okay, this is the velocity potential equation for compressible flow. If I have an equation like this, now what is ABC? A equal to
equal to 1 minus m square.
m square, and B equal to 0, C equal to 1. And what is B square minus 4AC now?
4m square minus 1.
4 into m square minus 1. So now how can I say whether it is elliptic, parabolic, or hyperbolic?
It's on the
Depends
mark.
on M value.
Depends
Mach
on
number.
yeah, Mach number. So if if it is subsonic flow, if m is less than 1, then B square minus 4AC is
Less than 0.
less than 0, and so this is elliptic. Okay, you remember that subsonic flows are elliptic in nature. And if it is sonic, m equal to 1,
Parabolic.
this is equal to 0, this is parabolic. If it is supersonic, m greater than 1, b square minus 4ac greater than 0, this is hyperbolic in nature. Okay, so supersonic flows are hyperbolic and subsonic flows are elliptic, sonic flows are parabolic. So that is the main problem. Okay, as I told once, if I want to solve the ICBM problem, something like this. So if I have a rounded nose, I'm going to have a shock like this. This is called bow shock. Okay, and there will be a region in which this is supersonic flow. Okay, so here I will have normal shock. Here I am having weak shock or oblique shock. Okay, this is oblique and this is normal. Normal shock is strong shock, and so here it will become subsonic. And oblique shock is weak shock. Here it will be still supersonic only, but if I take this M1, this M2 will be less than M1 here. Here M2 will be less than M1. Okay, everywhere M2 is less than M1, but still in this region, this is subsonic, and in this region, it is supersonic. And if I want to solve the problems, in this region, it is elliptic in nature, and in this region, it is hyperbolic in nature. So such equations are difficult to solve. It is steady flow when it is steady. If it is unsteady, I will have a time derivative there, and the whole equation behaves like parabolic, and I can solve it. Okay, so that's what I was discussing some time back. Okay, here, what is this? Why subsonic is like this, supersonic is like this? I will ask you one question. Suppose I am at a railway crossing, right? So I want to cross a railway track, and I am a blind person. Okay, I can listen, but I am a blind person. I want to cross it. So if a train is coming from far away, I can listen to the sound because these are subsonic things. The sound comes faster than the train, and I can listen to the sound, and I can comfortably cross. I can understand where it is very far, and I can cross it, and I can go. Is it clear? Because the sound waves come later to the before the train comes. Okay, it is something like this. If a train is here, okay, and it is making some sound, right? It is making some disturbance in the surrounding, and so the disturbance travels like this. So after one after 1 second, it goes to a distance of maybe u. Okay, the sound travels to, the disturbance travels a distance of, if sonic velocity is a, it travels by a. Am I right?
Yes, sir.
And 1 more second if it goes, then it goes to this point. So 1 more u it will go. And the disturbance that is made here, the first disturbance will go to 2a, and the second disturbance it goes to distance a. Okay, like this. And if I see it after some 5 seconds or 10 seconds like that, what happens is, it will be something like, this. The sounds, I think I can show you a slide maybe there, I think. Yeah, this way it will be. So when it is here, the first sound wave, it goes very far. Second sound wave, it comes like this. And third sound wave, it comes like this. Am I clear? So all of them, it will be, the circles, the sound waves will be like this. Is it clear?
Yes, sir.
Okay, so this is called as zone of disturbance. And this is called as zone of silence. And always this body will be within the zone of disturbance. Am I clear? And so there is a particular, everywhere the disturbance goes uniformly in all directions. Okay, this is elliptic in nature. But suppose now I want to cross it, and it is coming with sonic velocity. It is coming with sonic velocity. So can I listen to the sound before it comes?
No, sir.
No. Actually, the sound and the train travel together. Okay. So I cross and it hits it. When I hear the sound, it hits it. It hits me. Okay. That is called. And so here what happens is, it will be something like this. And all of them, all disturbances will be like this. And the train initially here, it comes and it comes with the wave. And all these waves together, because all the disturbances join together, it becomes like a shock almost. And it travels with the train. And so this side, it is zone of silence. Nothing, if you are standing anywhere on this side, you will not listen to this. This is zone of disturbance. And this is the real characteristic. Okay. So the whole region is divided into two parts. One is zone of silence, another is zone of disturbance. It's a single line. Am I clear about it?
Yes.
Yes, sir.
Yes, sir.
Okay, this is parabolic in nature. So if it is traveling with sonic velocity, it will be like this. If it is going with supersonic velocity, then what happens? The train goes faster than the sound. Okay, so it will be like the disturbances will be like this. The first disturbance goes this way. The train has gone to this like this. And this is the a cone-like thing happens, and the zone of disturbance is like this, and the zone of silence is this. Is it clear? These are
Yes,
the two real characteristics. If it is 2D, okay. So if it is 3D, it will be like a cone. If it is 2D, it will become like this. Two real characteristics. And so suppose if you are standing here, What happens is, though this is crossed you, I will not listen to the sound if you are in zone of silence. Many times what happened, no? Suppose you are in a home, in my childhood it used to happen. You are in your home and you listen to the sound of a aeroplane and you go to the terrace and you will see the plane and you can see crossing you slowly. Sometimes you will listen to the sound and come up. You will see that the plane very small and it is already gone far. If it is a turbojet like thing, so what happens is you will not listen to the sound before it comes to you. You will hear the sound only after leaving you, after some time when you are in the zone of disturbance. Similarly, suppose you are in a small boat and big ship goes there, a little bit far away. And when the ship is coming, nothing happens to you. When the ship crosses, actually ship makes the disturbance in the same way, whatever I have drawn for this supersonic flow. Okay, it makes the disturbance like that. When those waves reach you, then your boat goes up and down. Am I clear?
Yes, sir.
Okay, so this is a supersonic flow. It will have two real characteristics, and this is hyperbolic in nature. Okay, this is the way I can classify a two-dimensional, the second order derivative equations. But suppose now I have simultaneous equations because I have continuity, momentum, and energy equations and all. Suppose I have simultaneous first order equations. So actually I have simultaneous second order equations, finally physical things, but I will go slowly. If I have simultaneous equations and simultaneous first order equations, and how to classify them, I will quickly go through like this. Okay, and if it is like A1 ux plus A2 bx, there are two dependent variables and two independent variables. Dependent variables u and v, independent variables x and y. Okay, so A1 ux plus A2 vx plus A3 uy plus A4 vy is equal to some f1. Similarly, B1 ux plus B2 vx plus B3 uy plus B4 vy is equal to f2. Like this, I have two equations. Okay. And so how to classify them? These two equations, whether it is elliptic, parabolic, or hyperbolic, how to do it. So what I do is I will write this in matrix form. A qx plus B qy is equal to f. Okay, so where q is equal to the dependent variable matrix uv. Okay, and so qx is ux vx, qy is uy vy. And so here, what is the A matrix from the first equation? A1, A2. Okay, B1, B2. Into actually, I have ux, vx, right? Plus A3, A4, B3, B4 into uy, vy is equal to f1, f2. Am I right? So q is equal to uv, and this is A, and this is B. Am I clear about it?
Yes, sir.
Okay, this is the way I can write. And now the same, okay. Here, how to define the characteristics is, I define T is equal to A dx plus B dy. If the determinant of this equal to 0, right? If I use that, so then what happens? This is the equation of the characteristic. Okay, And so I will have A is A1, A2, B1, B2, dx plus A3, A4, B3, B4, dy is equal to 0. So what will I get is A1 dx plus A3 dy, A2 dx plus A4 dy, B1 dx plus B3 dy, B2 dx plus B4 dy equal to 0. If I take like this, if I expand this, what happens? Dy whole square, what will I get? Dy whole square into A3 B4 minus A4 B3. This I will get plus dy dx into, so what will I get? A1 B4 minus A4 B1 plus one more thing I will get, A3 B2 minus A2 B3. Am I right? A2 B3, A3 B2 dx dy into, plus dx whole square into what is that I will get? A1 dx into B2 dx, A1 B2 minus A2 B1. Like this I will get. That is here dy whole square plus I think I will put minus. Okay, like this. If you take this as some p, and if you take this as q, and if you take this as r, right? So again, dy by dx whole square into p into dy by dx whole square minus r dy by dx is q okay, like this we will get. So similarly here dy by dx is equal to r plus r minus root of r square minus 4pq. Okay, like this. Here again you will get r square minus 4pq, either less than 0, greater than 0, equal to 0. You will have elliptic, parabolic or hyperbolic in nature. Okay, so this is the way we will get. So this p is nothing but the coefficient of the determinant of this matrix, and q is nothing but the determinant of this matrix, and r will be, you have to take this first and last columns minus this second and third columns. I have to take like this, and based on that we have to classify. So next class we will see some examples for this, and then we have to see if it is second order simultaneous equations, how to go about. Okay, this is one method, and the other method is, if I write this as ADX, sorry, 2x. If I write like this, I can multiply by A inverse. It will become QX plus A inverse B QY is equal to A inverse F. And this A inverse B, you take it as some M. Okay, and find out the eigenvalues of M. behavior of the equation. If all eigenvalues are imaginary, this is elliptic. If few are real, then it is or if real values are less than a number of equations, then it is parabolic. If all are real, then it is hyperbolic. Sometimes you will have mixed equations also. There may be elliptic and parabolic like that. We will see next class how the classification can be done for these types of problems. Is it okay? There are two methods. This method can be done and that method can be done. Based on the convenience, we will prefer. And usually this is done only when you calculation of inverse is easier. Otherwise, we will go to the previous method only. Okay, we will continue in the next class. Any questions?
No, sir.
Sir, like if there are all three dimensions and the time is
Yeah, any number of equations, no problem. These simultaneous first order equations only it should be there. I have done for 2 equations, but these methods are valid for any number of equations, 3, 4, 5 or anything.
okay.
So we will do tomorrow, our next class, the more number of equations, either 2 or 3, like that. We will do some examples. And so quickly, I will just go through the slides. You go through them. So these are analytical solution. Okay. Equilibrium or jury problems like steady state temperature distribution, incompressible invisible flows, equilibrium stress distribution in solids like that. And these are domain for equilibrium problem is or jury problem is fixed. And example problem is something like this. If you have a rectangle and if you are solving this del square t equal to 0, so prescribing the boundary conditions like that. This is one example. And analytical solution from heat transfer, you can see this is this. And eigenvalue problem like buckling problem, stability of structures, resonance, and natural frequency in vibrations. These are eigenvalue problems. And they occur infrequently in fluid mechanics and heat transfer. They are not discussed here. They occur in solid mechanics problems. And matching problems, these are called initial value problems or initial boundary value problems. Okay. And so we have seen the discussions. So this like open domain for matching problem. So if you are given initial condition, I can find out how the values change in time. Okay, like that. And this is the example problem again. And hyperbolic, this is the wave equation. And the wave equation, okay, one small thing I want to tell. Okay, ut plus aux equal to 0. This is also hyperbolic because this is the first order wave equation. We can get second order wave equation from the first order wave equation because ut equal to minus aux. If you differentiate this with respect to x, with respect to t. So utt is equal to minus a. This x and t I will interchange. uxt I will write it as ut of x I will write because x and t first this or first second that it doesn't matter. And ut I will substitute ut equal to minus AUX. So minus A minus AUX of x. So this will become A square UXX. So this will be UTT is equal to A square UXX, which is second order wave equation. And I know that this is hyperbolic. So this first order wave equation also is hyperbolic. Yeah. Is it clear?
Yes.
Yeah. So this is a second order wave equation. And so here, these are the examples for marching problems like unsteady inviscid flow or steady supersonic inviscid flow or transient heat conduction and boundary layer flow. So I told you boundary layer flow also, it is marching method, you can solve it. So because of that, here, one-way coordinate is x coordinate. So this is the thing we have done. So these are elliptic equations. These are parabolic equations. These are hyperbolic equations. And this is the way we have done that. And different model equations here. So we can, based on that, b square minus 4ac, you have to tell whether it is elliptic, parabolic, or hyperbolic. And this is the first degree equation, what we have done today. Okay, the description is not there. Okay, whatever we have done here. So this is done in a different fashion. I will not show here. I will send you whatever I have done today. Okay, and sorry. So we'll go for the story quickly. This is about Glenn Cunningham. Have you heard about him? So it's a good story. Once a young schoolboy was caught in a fire accident in his school and was assumed that he would not live. It's a real story. And his mother was told that he was sure to die, for the terrible fire had devastated the lower half of the body. Even if he were to survive, he would be a cripple throughout his life. That's what is told. But the brave boy did not want to die, nor did he want to be a cripple. And much to the amazement of the doctor, he did survive. But unfortunately, from his waist down, he had no motoring ability. So he cannot move. His thin legs just dangled there, lifeless. Ultimately, he was discharged from the hospital, but his determination to walk was indomitable. At home, when he was not in the bed, he was confined to a wheelchair. One day, he threw himself from the chair and pulled himself across the grass, dragging his legs behind him. He reached the picket fence, raised himself up, and then, stake by stake, he began dragging himself along the fence, and his resolve to walk was undeterred. He did this every day. It is so painful. Now, for reading, it is so easy, but how painful it is, only he can know. He did this every day with faith in himself that he would be able to walk unaided. With his iron persistence and his resolute determination, he did develop the ability to stand up, then to walk haltingly, then to walk by himself, and then to run. It took years, but every day he struggled like that. He began to walk to school, then run to school, to run for the sheer joy of running. Have you seen this one movie? It's got Forrest Gump. Have you seen that?
Yes, sir.
Yes, sir.
Fantastic movie, right? He's
Yes, sir.
he has got a polio leg and all, and then he runs later. Okay, I liked that movie very much. So he began to walk to school, then run to school, to run for the sheer joy of running. Later in college, he made the track team. In February 1934, in New York City's famed Madison Square Garden, this young man who was not expected to survive, who would surely never walk, who would never hope to run, this determined young man, Dr. Glenn Cunningham, ran the world's fastest mile, an epitome of the power of positive thinking and faith in oneself. Glenn Cunningham continues to be an inspiration for many and his story a brilliant testimony of how one can bounce back even when all odds are stacked against one, to the extent that death seemed the preferable option. Okay, he is this fellow. In running, it is man against himself, the cruelest of opponents. The other runners are not the real enemies. His adversary lies within him, in his ability with brain and heart to master himself and his emotions. He is his record. Actually, it is 4 minutes, some 2 seconds or 3 seconds he has taken for one run, uh, 1 mile to run, and for many years it is not broken. Actually, he wanted to have what is called as 4 minute mile. Okay, his target is to complete in 4 minutes. He tried and tried, but he could not, and his that record was not broken for many years, and people thought nobody can run a mile within 4 minutes. But later it is broken by many people. Right now it is, I think, 3 minutes 47 seconds is the record. So it is one example for evolution. I really believe in evolution. That is the capacity or capability of the persons increase continuously. People say the latter generations will be weak and weak and weak. No, nothing like that. So in previous generations, what used to happen is it is like survival of fittest. At the time, medical things, science are not developed. Only the people who are fit only used to survive, and all others used to die. And only the fit persons are available at that time. But now, what happened is there are many people who are not fit, but they are made to survive by medicine. That's why, in average, people see that many people are weak, but the strong people are more stronger than the previous generations. Am I right or not? All records are broken
Yes, sir.
every time, right? Because there are more capable people, not only intellectual but physical also, right? The evolution is there. I believe it. Every time the records are broken, any record, whether it is an intellectual or physical capability. Okay. Okay, thank you. And this is one inspiring story. I liked it very much. So, and next Monday, again, we will have a test in LMS. And till now, till this class, whatever is covered will be there in the minor, second minor.
Okay, sir.
Right? Okay, thank you. I have to stop recording.